So, as we said, the previous lecture was about the derivation of the uncertainty principle, right? We used like if we want to measure something, right? This was a start. If we want to measure something, right? For example, some system in a state, in some state, and we want to measure its momentum. So quantum mechanics will give us a value from many of the possibilities, right? And what we get will be a single value out of all the possibilities. So to make quantum mechanics according to our experimental lab, we use the expectation value or the average value, right? So the average value of one operator in Brownian notation, if we have operator omega, if we have another operator, like we have position and momentum, right? So one we have x, and then we have p as well. We want to measure the momentum of the system, right? So there will be uncertainty in momentum, uncertainty in position, and the uncertainty in position and momentum can be defined from the standard deviation, definition of the standard deviation, right? That is, the uncertainty square is equal to average of the square of the operator minus square of the average of the operator, right? So we put that definition into action there, and you know what we get is the uncertainty principle as a result, and we know that the two operators will have some commutator, right? We know that if the two operators commute, if we want to find the position of a system and then again the position of the system, so x and x commute, and we don't have any uncertainty principle at all. The uncertainty principle will be involved only when the operators do not commute with each other. For example, the position of the system and the momentum of the system, right? So in that case, we say that the product of the uncertainty, right, delta omega and delta lambda, which we said, the product of the uncertainty of the two operators or two observables will be greater than or equal to h cut over 2. So there is a lower limit to it, and that is h cut by 2. The product of the two cannot come, below h cut divided by 2. So there is a lower limit that we can get the product of the uncertainties of the two operators. We will have some value of the uncertainty. We cannot find certainly this pair. We will have some value of uncertainty, and there is a theoretical limit to that, right? So we said the last thing was delta omega, right? And delta lambda greater than or equal to h cut divided by 2, right? And we said that the equality will hold. The minimum limit will hold only if, right, there was something anti-commutator. right? So the equality will hold only if omega and psi is equal to c into lambda into psi. If one operators can be written in terms of the other, and if there was another thing which was called the commutator, right? We call this as the commutator. We said if this is equal to 0, the expectation value of the commutator, if this is equal to 0, and if omega can be written is like a constant time, it is a constant, see, a constant time, the other operator. So in these two situations, if our system qualifies these two conditions, right, then we will say that that delta omega delta lambda will be equal to h cut divided by 2. Right? Now, we can find out what is that state for which the uncertainty product is the minimum, for which the product of the uncertainty is the least. We can find out that that function, right, for which this thing will hold. We would call, or we call this the minimum uncertainty package. The minimum uncertainty package. Huh? We can use these two conditions because the minimum is here subject to these two conditions. So we can use these two conditions. If this is number 1 and this is condition number 2, we can use these two conditions to find out what is that wave function, what is that state for which the uncertainty between two operators or observables will be the smallest. Like if we have, for example, two operators, omega suppose is equal to x, right? And lambda is equal to p, right? We use the coordinate space, right? In coordinate space, the momentum is defined as, right, I at d by dx. This is how momentum is defined in the coordinate space, right? So by using these two equations, this would be like xp plus px, right? This will operate on this. So here, p in the coordinate space will become a differential operator. This will give us a differential equation, right? And by solving that differential equation, d psi by dx. By solving that differential equation, we get this wave function d psi by, like you solve a dy by dx differential equation, you get the value of y. Similarly here, you solve the d psi by dx equation, you get psi. The psi that we get for the state, right, where the uncertainty is the least, the product of the uncertainty is the least. That comes out to be the Gaussian function, right? It comes out to be the Gaussian function. You know the Gaussian distribution. If we do this and solve this equation with this condition in the coordinate space, we get a wave function. For psi of x, we get a function in space, and that function, it comes out to be psi of x is equal to psi of 0 e to the power I p x over h and e to the power minus c x square over x squared to h squared. Right? This is the equation that we get. And this is the equation for a Gaussian function, right? Where the mean value is at 0. The origin has been brought to 0. So the mean value is 0, and that is the peak, the amplitude, right? And we can say what will be the width of, a Gaussian function is something like that. A Gaussian function is something like that, right? And this is called the mean value, and this is called width of the function delta sometimes, right? So this function can further be written in to bring delta, the width of the function, into the equation. So suppose we define delta is equal to h over c. Right? Suppose we define delta square is equal to h over c. So h over c is here, right? So we will revert that, like delta would be come here in the denominator, right? So we can write psi of x is equal to psi of 0 and e to the power I p x over x e to the power minus x squared over 2 delta. The delta is the width of the Gaussian function. So if we have a system in a state such that its function which defines the state, it is a Gaussian, then the uncertainty will be the least. The product of the uncertainty for x and p will be the smallest. सब बहुत ही कम शकूक को शुबहात होंगे फिर और की theoretical limit वही है कि इसके बराबर होगी क्या इसके बराबर right? So this is for your information to know that what kind of function should be having the minimum uncertainty function. Sometimes people call it a wave packet. It's kind of a packet. Now, the uncertainty principle is a very interesting tool in our hand. We can use it in different situations, like we used it in dealing with the harmonic oscillator problem. We used uncertainty principle there. There are other uses of uncertainty principle too. We can get very good approximations. Approximate values that are very close to the experimental results without much difficulty, without much labor. We get the results of observables of our experiments without doing a lot of computation, a lot of labor. Now we see how can we use the uncertainty principle to a hydrogen atom, right? Applications of the uncertainty principle, right? Suppose we say find the radius and energy. We say ground state energy. Suppose of a hydrogen atom, right? Suppose we have a hydrogen atom, a single hydrogen atom. Let us apply the uncertainty principle, right, to get to see what is the result if we want to measure the energy and radius of the hydrogen atom in the ground state. The ground state means when it is in the lowest possible energy state, the lowest energy, right? And we know that if you remember, there was energy of the ground state energy of the oscillator as well, right? If you remember, it was half h cut omega, right? That was the ground state energy, the minimum energy of the harmonic oscillator. We said that it was not equal to 0. So let us see what is the energy of the hydrogen atom, the least energy, the minimum energy, the smallest energy of the hydrogen atom, and the radius of the hydrogen atom. So suppose the hydrogen atom is in a state psi, right? Some state. right? Okay, so we have this hydrogen atom. That is the nucleus, and here is some electrons. Suppose we say it is revolving, or in quantum mechanics, we actually don't say we don't. In quantum mechanics, we don't have clearly defined orbits, so we don't have this. But I'm just giving you a rough picture. So the energy, we say this atom is at rest. In the ground state, we say this atom is at rest. So the nucleus is at rest. The electron is attached to the nucleus. So to find its energy, we will have to measure the Hamiltonian of the system, because Hamiltonian gives us the total energy of the system, right? So we will have to find the Hamiltonian of this, and the Hamiltonian of this is kinetic energy plus potential energy, right? So if this is at rest, we neglect the nucleus. Suppose we neglect the nucleus because we say the nucleus is at rest, and the only function of the nucleus is to provide to the electron. It provides the potential energy only. It keeps the electron revolving in a very rough way, suppose. So there is we can take nucleus out of the picture, because we suppose the atom to be at rest and the electron in motion or under the attractive force of the nucleus, right? So it will have two terms for energy, and that will be for the electrons, right? Only the electron, not the nucleus. So it will be p squared divided by 2m minus e squared divided by some radius, right? And if we want to write this in terms of the operators, right? So we will write them in like that. X squared plus y squared plus z squared, right? That is the Hamiltonian in terms of the x and p operators, right? Or we can say that this is further equal to px squared plus py squared plus p z squared divided by 2m minus e squared divided by x squared plus y squared plus z squared. These are in the form of quantum mechanical operators, right? Okay, so we are going to measure the energy of the hydrogen atom. So in quantum mechanics, we will say that will be the expectation value of the Hamiltonian. If we are going to measure the energy of a hydrogen atom in our lab in quantum mechanics, that will be equivalent to measuring the expectation value of the Hamiltonian. So the expectation value of the Hamiltonian will be like this, right? Px squared plus py squared plus pz squared divided by 2m, no, no, sorry, minus e squared divided by x squared plus y squared plus z squared into that, right? Okay. Now we can write them. X is equal to what? P x square plus PY square plus PZ square and divided by 2M, right? Minus E square divided by square root of X square plus Y square plus Z square. This is, we can spread the average in situation, right? Now, we can write this is this is actually, we cannot bring this. We lost connections. Can you see me now? Aftab? Aftab?
Yes, sir. Yes, sir. I can see.
Oh, so you see me now?
Yes.
Okay.
Yes, sir.
Okay. So now this by bringing this expectation, this mean sign, the average sign, to here to the denominator, it is not completely equal to this, but if we can say it is nearly equal, right? So the Hamiltonian is nearly equal to. I can write them as px squared plus py squared, right? This mean of the square plus pz square mean divided by 2m. But this one, because of this, the further the next step, I am using the nearly equality sign, right? So minus that will be e square, I'm writing square, and I bring the two average sign here. X square plus y square plus z square. Right? Now, I further want to write the right minus e square divided by right square root of x square. Again, this is not equal, but I'm taking the equivalent sign. Yeah, there's a little bit difference. Plus y square plus z square divided, right? Let me write these things here. That would be like p x square plus p y square mean value plus p z square mean value divided by 2m. Well, this is equation number 1, right? We have mean of the square, 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 right? So we can use the definition of the standard deviation to bring, remember, if we want to use the uncertainty principle somewhere, we have to bring the uncertainty turn from somewhere into the into solving our problem, right? So therefore, we use the standard deviation concept to bring the uncertainty into the into x and p, right? And the standard deviation is like delta p squared, right? That is equal to square of the mean of the square minus square of the mean, right? Our p, so here this will be equal to delta p squared, right? Delta p squared plus here square of the mean. right? So we will replace this here. Look, p square. This is p square, p square average. This p square average. We will replace this by these things, right? So px squared, right? That will be equal to delta px squared and plus b of px squared. Similarly, py squared will be equal to delta py whole square and plus py b square. Similarly, p z squared that will be equal to delta pz whole square plus p z mean square, right? Similarly, x, other operator, we can do the same thing with x. So x squared will be equal to delta x whole square plus x average square. Y square average will be equal to delta y whole square plus y mean square. Similarly, z square average is equal to the uncertainty in z whole square plus the mean value of z and squaring it to be squared, right? Now, since we are interested in the lowest possible energy, right? This is the definition in px square, py square, p. The average value of px square, py square, pz square, and x square, y square, and z square. We can put it there. Look, px square here. We will put this here. For py square average, we will put it here, this thing. For pz square, put it here. For x square, put it here. For y square, put this here, put this here. So we will have a long equation, right, in which we will have these terms: p x square, p y mean square, p z mean square, x mean square, y mean. Let us take, let the state is like, since we are interested in the mean, so let us suppose the states is such that the mean is equal to 0. The mean is equal to 0. We have to minimize this. We have to minimize this value because we said the ground state energy. Find the ground state. So we have to go to the lower side, lower, lower, lower. So how can this be made the lowest? The least is by thinking that this is equal to 0 and this is equal to 0. This is equal to 0. This mean is equal. Here's the mean. The mean can be 0, right? If we have a hydrogen atom, right? So if we want to suppose this position, right? So this is plus y and this is suppose minus y. So if we take the mean of them, we will get what? 0. So we are not violating some strict mathematical rules. So the mean can be equal to 0. If we select our origin appropriately, अगर हम अपनी origin को intelligently use करें और place करें, so we can get these equal to 0. Right? So when these are all equal to zeros, right? P square, sorry, not P square, P average square is equal to X average square is equal to Y average square is equal to Z average square, and put that equal to 0. Right? For minimization, for energy minimization, because we want to minimize the energy. So that is equation number 2. So use equation 2 into 1. For px square, we should write here delta px square. For py square, we should write delta py square. For pz square, we should write delta pz square. For x square average, we should write delta x square. So we put this situation along with this set. I will call this set as S, a set of equations. So using the set of equations S and 2 together, right? Equation 1 can be written as, equation 1 can be written as at expectation value, right, is equal to, so that will be that form, 3x squared plus delta py squared plus delta pz squared divided by 2m, right, minus e squared divided by square root of, right, delta x squared plus delta y squared plus delta z squared. Right? So we got a new equation. Right? We got a new equation. Oh no, ये हमारे काम की है. This is good for us. This is useful now. This the Hamiltonian, not the Hamiltonian. The expectation value is in a useful format. Right? So, look, this is equation number 3. We assume, now this is the good equation, we can further simplify it. We assume the hydrogen atom to be spherically symmetric. So when it is spherically symmetric, right, then delta x square can be taken as equal to delta y square, can be taken as equal to delta z square. Right? So assuming X to be spherically symmetric, if we assume that, then delta x square will be equal to delta y square will be equal to delta z square, right? And p delta p x square will be equal to delta py square will be equal to delta pz square, right? So suppose we take this form of this equal to delta x square. So we put this here, we put that here. So what do we get? The Hamiltonian is equal to, right? It will be 3. So 3 delta p x whole square divided by 2m, right? Minus e square divided by, right? Will be 3 2. So it will be their roots. 3 and the sum x whole square. R can be like 3 by 2m and 2 delta px square minus e square divided by 3 square root and 2 delta x. Right? That is the question number 4. Right? So now it is easier for us, right? Easier for us. We have this, we have this thing. So let us replace delta px by delta x using the uncertainty principle, right? Huh? Delta x, delta px is greater than or equal to h cut over 2. So what we will get is delta px is greater than or equal to h cut divided by 2 delta x, right? So we use this point in equation 4. We use equation 5 and 4. What we get, the expectation value is equal to, right? 3 by 2m and h fact square divided by 4 and to delta x whole square, right? And minus e square divided by 3 square root and to delta x. This is number, suppose it is number 6. Now this is energy of the hydrogen atom is a function of x or delta x, right? So if we want to find the minimum radius of the hydrogen atom, we should, this is an equation of delta x. We should take the derivative of this and put equal to 0. Because when you want to find minimas or maximas, you put the derivative or differential equal to 0. So we differentiate equation 6 with respect to uh, and put this equal to, right? So when we do that, the right hand side, this, right? This is equal to minus 6 over 8 m and 2h squared divided by delta x whole square and plus e squared divided by 3 square root and 2 delta x whole square, and here it's not square, it's 3. This is whole square and this is 3, right? You differentiate this with respect to delta x, so the power will become 3. And you multiply it with this 2, and the 2 times 3 will become 6. Similarly, this will become delta x squared, and the minus will become a positive. So here, I get delta x from here. So delta x will be equal to 3 by 4, right? And to 3 square root and h square divided by m into e square. And this is nearly equal to 1.3 to h square divided by m e square to delta x. Well, the experimental radius, right, of the hydrogen atom in the ground state, we can see uh, is equal to h square divided by m e square, right? To the average from, you can say we compare it with our experiment, suppose. So that is this one, right? So there is a very small difference. Establish radius. Very close to the established radius. Only the difference is 1.3, a multiple of 1.3. So if we want to find the approximate values of observables, we can very successfully use the uncertainty principle. So we can see that this is the established value, this is what we got from the uncertainty principle. The only difference is an excess of 0.3 factor. Very close, right? Similarly, we can get the element of the So the uncertainty is of the order of the radius of the hydrogen atom to ground state. Right? Now, if we put this value of x back into that equation number 7 greater than or equal to 7, we put this value back in that equation for the expectation value of the Hamiltonian. It was like that, right? Something like H is greater than or equal to 3 by 2 m H square divided by 2 delta x whole square minus t square divided by t square root m delta. Excellent. So we put our result for delta x today, right? So we get what? We get the potential value, right? This to them are equal to, we put delta x value this thing here. What equation should I say with this? Some equation number. I just erased them. So the energy is greater than or equal to, we put this value from here. What we get is minus 2 by 9, right? And E4 divided by H cut. Okay. This is, approximately equal to minus 1 over 4 and E4 divided by H cut square. Right. This is what we get the expectation value of the energy. Right? Expectation value of the energy, we get this, where we know that the energy of the hydrogen atom in the ground state, the established value, right, is minus the established value is E ground, right, is equal to minus M4 divided by S2H factor. Right? So, this is the established value, and this is what we get from the uncertainty principle. Right? It's very close to this. It is just half of this. Our value is half of this, so very close. So if you want to approximate values of different observables, using the uncertainty principle can be a useful trick, right? This is very close to the Bohr radius. This is the Bohr radius. This is very close to the Bohr radius. This is very close to the ground state energy. So these are the applications of the uncertainty principle. Let us hope that we will meet in person next week, and see you everyone in good health. If you have any question, you can ask me now. Otherwise, I am going to finish today's lecture.
Thank you, sir.
Okay, sir.
Thank you. Bye bye.
Thank you much.
Bye bye. So you people should leave so I can close the meeting.
Sir, thank you.
Thank you.
Assalamu alaikum, sir.